when we talk about mechanical advantages, we're talking about the number, the numerical value by which something gets harder to do if the mechanical advantage ain't so great. And if the mechanical advantage is great, how easier it is for you to do something or accomplish a task by using that machine. Does a wheelbarrow make it easier for you to lug big things around? It does, so that class 2 lever is going to have a higher mechanical advantage. Okay? And we're going to see that some machines have no mechanical advantage at all. But we use them in certain situations because they don't make it easier to do something, they just make it possible to do something. You still have to put a lot of effort into it, but you're going to actually get it done. Whereas you might not be able to get it done without using that machine. Okay? So mechanical advantage looks at the number of times that any simple or complex machine is going to increase or decrease the effort force required to accomplish a task. And the equation is quite simple. It involves the relationship between two things you already know. Okay, so the mechanical advantage, I'm just going to call it MA. MA, mechanical advantage, is going to be equal to the load force divided by the effort force. And I know that some of you right now are like, well, how do I know what my load force is? How do I even know what my effort force is? You can measure those things. Okay, granted, if I'm playing tennis and I'm swinging my racket and hitting a ball back and forth with somebody else on the other side, I can't sit there and measure my amount of effort every time. But in a lab situation, you can actually measure the amount of effort required to lift something off of the ground. You can also you can always calculate the load force. Because the load, we know that the load is the object you're dealing with. So in the case of my example of my class 1 lever over there with my bar, okay, my fulcrum, and it's got my little mass here, right? That mass is made up of a certain amount of atoms. If I take that object's mass, I can measure that. And if I have an object's mass, I know that its weight is going to be equal to the mass times the gravitational constant. Right? And weight is a force. Your weight is your load force. So if you can calculate the load force of any object, all you've got to do is figure out its weight. If that little mass over there is a 200-gram mass, 200 grams, we know that to calculate the weight of something, which is a force, right? Force is equal to the mass of the object times gravity. F is equal to m times g. We know that mass is always in what unit? Kilograms. Okay, now here's the trick. What did I tell you the mass of my object was? It's in grams. So you have to convert that. So all of the stuff that we've learned so far is coming into play here. Okay, this mass has to be converted to kilograms. And we know that kilo means 1,000. There are 1,000 grams in 1 kilogram. So if I'm going to actually do this, if I've got 200 grams and I want to change it to kilograms, okay, if I'm going from something that is small to something that is bigger, because a kilogram is bigger, and it's 3 hops away from grams, because We go gram to decagram, decagram to hectogram, hectogram to kilogram. That's 3 hops. So if we multiply this by 10 to the power of -3, right? Negative because we're going to the left, that's equal to 0.2 kilograms. You did all this in your conversions. You've seen this before. Multiplying it by 10 to a negative exponent is the same thing as dividing it by 10 to a positive exponent. Same thing. Okay, you know this. So if I've got the mass now of my object in kilograms, I know that my 200-gram mass, 0.2 kg, is going to be multiplied by the gravitational constant. 10 newtons per kilogram. My kilograms cancel out, and I'm left with newtons. That's amazing because a force's units is newtons. So we end up here with something along the lines of 2 newtons. My load force here is going to be 2 newtons. My effort force is going to be measured using a spring scale. Remember I had you drag stuff along, masses along different surfaces and you were reading the spring scale? You were calculating, you were measuring the effort force required to move it across that surface. The bumpier the surface, the more friction the surface, the higher the amount of effort you needed to drag the object across that surface. Okay, so you can measure your effort force using a spring scale. You can calculate your load force. You can also measure your load force on a spring scale and get that. If you know those 2 values, you can then calculate your mechanical advantage.